where everybody visit your website. And if let's say you are taking data from it, most of the data are stored inside the database. So your front end web application is going to access the data in the back end, which is only one server. Okay? And this might not be good for several reasons, which we will touch later. Now on the right hand side, we try to improve it. Okay, we improve it by increasing the number of servers. So we have a database with several servers. Now the front end, whenever you have any request from the user, you will go to the back end and you select from them. Okay, whichever database that contains the information, you retrieve the data from them. Okay. Now here there are several advantages that we can get from having distributed database or distributed system kind of database. First thing is we can see from here that the database has their own specific role. Okay? On the database tree, you see that it contains the information about the user. Okay, the user, let's say log in, you need to log in, right? So you ask for database tree, and that database tree only has that specific role to store information about the user. Then you request the information from the user, let's say password and everything. And because you have to authenticate, right? Make sure that the user that logged in is the correct user or rightful user, not any hacker. So if the user key in the correct password and you check with the database is correct, then only it will access the other database to retrieve the information. So the other database maybe contain the web pages or the data or file that is related to the application. Okay, so in that distributed manner, you can see that the role of the database can be assigned. Okay, one row is assigned to one database. It's more well organized. Okay, another thing is you can have replication. Let's say database tree, you can have database tree A, tree B, for example. So tree A and tree B will be storing the same information. Why do you need to replicate? Let's say, for example, database tree server is down. Now you can access tree B. It will contain the same data, right? Whereas in the traditional database, you cannot do that. If let's say database server is down, everything is down, including the information that you want to retrieve. It's also get destroyed. Let's say the server is completely destroyed by fire, for example. Okay, another good thing about distributed system is that you can put it in one specific location or distributed across different countries. Let's say this one, database tree A is in Japan. Okay, and tree B contains the same information. It is not in Japan but in Malaysia. Okay, why is it good? Let's say, for example, Japan, you have earthquake event that is very often, right? If let's say earthquake happens, then power cut, for example, or the facilities is destroyed, that means your data is gone because the facility is destroyed. But your web application is still able to retrieve the information from Malaysia database. Okay, so distributed system appears to provide you better solution compared to traditional database. This is one of the main reason most of our application or system we tend to use distributed system rather than single system where we have everything on the same system, and if anything goes wrong, we cannot recover or the fault. Okay, so why important? Because customer when you have downtime, very long downtime, they'll complain, right? Even 1 second, 1 second maybe is okay, maybe 1 hour, they'll complain. Okay, if you have distributed system like this, you can switch of course your web application needs to be smart. When it cannot communicate with or the link is lost to the main database, you switch to the other database in other countries in order to retrieve the information. Okay, the basic concept I mentioned just now is basically the advantage of what we have for the distributed system, but of course the details is what is shown there. It involves various components in order to make it work. Firstly, you need to have operating system that is also capable of doing the distributed system or aware of the distributed system. Because if it is not aware of it, it will not know that the data is actually stored in different places. Okay, and you need to have a file system that is also distributed kind of system. Like for example, network file system, right? Not the file system that we have on our current operating system, which you can only store it on your hard disk. But you need a specialized kind of file system which is able to store the information at different places or distributed manner. And of course, when you talk about file system, we also need to talk about database. They are kind of the same, except that database you can use query language. Query language is quite powerful. Let's say, for example, you use SQL query, right? Everybody here learned SQL before? Have you learned SQL language? SQL. Yeah, SQL, right? So SQL is kind of programming language actually. You write in English and then it will retrieve the information for you. Okay? You can actually filter, you can select the table, you can form the table. Whereas file system you cannot do that. And that's why in business enterprise we seldom use file system to store data. We store data in database because it's much easier to manage. Okay, so database it needs to be distributed system aware so that it can retrieve the information from various locations whenever it needs the information. Okay. And of course, you need a way to also authenticate, make sure that the person who actually access the data is the person who he claimed to be, right? And you need to do it in distributed manner. Of course, you don't want hacker to hack into the system, right? So you must make sure that your distributed system is also able to authenticate and make sure that the data that is passed along is passed to the rightful person or authorized person. And you have to have your business logic as well. And this business logic will not run plainly on a single computer. It has to run on multiple distributed systems. Okay. And apart from that, you also need to make sure that you assign or load share your your process so that the server is not overwhelmed. Okay, it's not overloaded. Okay, imagine you have one server and then everybody is trying to access that one single server. You got 1 million customers to service at a time. If a single server, it will be overloaded, right? So if you have distributed system where you got multiple servers serving the customer, 1 million customer, then it will be much better service performance, right? Let's say you got 10,000 servers serving 1 million customers. So each server will handle some of the workload, okay, and you can serve the customer better, right? So distributed system has that advantage. You can do load balancing, and of course you have to allocate your resources carefully in order to allow you to do load sharing. So the benefit, I already highlighted some just now. These are the inverts. So you got scalability, meaning that you can improve the size. Okay, let's say you start small, maybe you got only 2 servers. Then, if let's say your customer increase, then you can scale it to bigger size. Okay, if let's say you already implement a distributed system properly, you can scale easily because it will be transparent, right? So every of the system is able to retrieve the information from their specific system which is distributed elsewhere. So you can scale easily if you have the system in place. Just now also I talked about reliability. You have duplication, right? So that is going to allow you to make sure that the system is able to recover quickly because you replicate it. If let's say the server is down, you can switch to the good server that is working, and the uptime is high, the downtime is low. You can also improve the performance, like what I mentioned, load balancing. So you got, that means you replicate as well, but this replication is on the service side. Okay, the customer wants to retrieve the data, they can retrieve from different servers, depending on where you are. For example, let's say in Malaysia, you've got a server in Malaysia, but the content, of course, is the same all around the world. Okay, so American will access their own American server. Japanese people will access the Japan server. But of course, you have to keep track, make sure that all the data is the same at all times. Okay? So you can increase the performance by having distributed system. Okay, you can geographically distribute your resources or your server into different locality, so that you can access faster as well. Let's say, for example, I'm in Malaysia. If I say Microsoft server, I access Microsoft server, it doesn't necessarily that when I type in Microsoft.com, I'll be accessing the server in America. Not necessarily like that, because of what I mentioned to you, load balancing. When it knows that my location is Malaysia, it will direct me to the server in Malaysia. But of course, that server is owned by Microsoft as well. Okay. So the benefit of scalability can be shown in this graph here. If you have okay, here there's two terms that is introduced, which is not clearly specified in this slide, which is vertical scalability, and then the other one is horizontal scalability. What does it mean? Vertical scalability means, sorry, I don't bring my pen here. It means you have multiple servers, okay, and they don't have to be powerful, but you have many of them. So if I want to increase the or I want to scale to larger size, I just add. Okay, I just buy the server. Okay, let's say I buy Dell server, and then if I want to scale, I buy more Dell server. Okay, so that is horizontal. Sorry, not vertical. It's horizontal. Horizontal scalability. Okay, if I want to improve the performance, another way, if I don't want to scale horizontally, I can scale vertically. Scale vertically means I have the computer and I upgrade the same computer to higher spec, maybe higher processing power, more cores, more memory, more hard drive on the same server. So that is vertical scalability. That means I use the same server, I just upgrade it. Okay? Horizontal scalability means I add new server. Okay, and this server need not be powerful, because you can group them together, right? And then it can give you higher performance because each one contribute their processing power. Okay, whereas vertical scalability, you only have the processor on the system, one system only. So if you want to increase the speed, you have to improve the processor. You have to buy a new processor. Okay, horizontal scalability, you don't need to. You can buy poor performance processor. You just increase the number. Okay, so let's look at the extra capacity, which is on the horizontal graph, and the vertical graph here, which is the price per capacity unit. So initially, you see that vertical scalability, that means you upgrade the server. You have the server and then you upgrade it. The cost appears to be very cheap when it is small, right? But when you scale to a certain size, you find out that it is very expensive, because here maybe it's supercomputer. Which company that has supercomputer? Very few, right? Very few company has supercomputer. So if you want extra processing power, maybe you need supercomputer, and supercomputer, you know that it's very expensive. That's why vertical scalability, if you want to scale very large, it's not a good idea, because it's going to be very expensive per capacity unit. Okay, every time you increase further and further, the cost will rise exponentially. Okay, the horizontal scalability is much better. You just add in the, let's say, Dell server, which you can buy off the shelf. Okay, if you need more, you just add more, right? Of course, it has its own disadvantage because you have more computer, you need more space. Of course, you need to make sure that they're able to communicate with one another. You need networking and all that. But price per unit capacity is much lower. It will not rise exponentially like horizontal scalability. Of course, when we talk about distributed system, we have to talk about the challenges. It looks nice on the graph and also from my explanation just now. But what are the challenges? So the challenges when we build the distributed system, we need to avoid single point of failure. Of course, we know that it can give us the redundancy. That means if some server fail, you can recover quickly. But how do you do it? Okay, so you need to implement the system. Okay, so in our case here, we don't centralize. That means we don't put our resources in one place. We scatter all around the globe. Okay, maybe we know that Japan has earthquake, or in Indonesia you got earthquake. You put some there because you want it to serve customer there fast, but you also put replication of it somewhere else in other countries, maybe nearby, maybe in Malaysia or Singapore. Okay, or maybe in, let's say for Japan, maybe in Korea or China. Okay, so that if anything goes wrong, we can recover from this single point of failure. Another thing is, how do you replicate that? So there's another challenge there. You want the advantage I mentioned just now, you need to be able to replicate. Of course, it comes with its own challenges. For example, what kind of operating system you use, and the cost of it, and how do you replicate it? You need some kind of algorithm to replicate it, intelligently replicate it. Okay, the next thing is you need to carefully allocate your resources so that you can have availability all the time, or uptime high, low time, downtime low. Okay, and also you need to allocate it at specific locations so that you can increase the performance. Let's say, for example, Netflix. If you watch Netflix from Malaysia, I know Netflix is from Western countries. Their server is maybe, their main server is maybe in headquarters in US maybe. If everybody is watching the same movie in Malaysia, let's say Korean movie, I'm pretty sure that some of you like Korean movie. You're watching the same movie, and everybody is accessing the movie from America server. So the streaming of that video has to be from America to here, and there are a lot of streams. Then it will occupy a lot of bandwidth, alright? Okay, it will choke the bandwidth from America to Asia because everybody is watching the same movie. Okay, so how do you increase the performance in this case here, or availability here? You can use content delivery system, okay, or CDN, where you replicate it. Okay, let's say you see that one person watched the movie, or maybe 2 persons watched the movie. It will replicate automatically from, let's say, US headquarters server. You replicate one copy in Malaysia server. Okay, so if the next person who is watching the same movie, it will come from this server rather from the US. So the streaming from US was only one time to the Malaysian server, and then the Malaysian server will distribute to all the customer in Malaysia watching the same movie. Okay, so that will increase the performance and also reduce the bottleneck of the streaming having to taken out by the video when you stream so many streams of movie across the Atlantic, okay, or across the continent. Okay, another challenges is resource naming. Just now I mentioned to you that you access Microsoft, right? You type Microsoft.com, and then if you have distributed system, you want it. If let's say I'm a Malaysian customer, it will redirect me to Malaysian server, right? It will not redirect me to American server, but to Malaysian server. So it needs to be intelligent enough to know that when I type Microsoft.com, it does not go to the American server. First, you find out where I am, and then you redirect me to the Malaysian server, even though it's Microsoft.com. Okay, so American Microsoft.com and Malaysian Microsoft.com will direct us to different server. Okay, so this will have something to do with resource naming, because you need to somehow redirect the person to the correct server to improve the performance and also the availability. Okay, and of course, something related to resource naming is the binding, because once you get connected to the server, that means your port is actually bound to the server that you're that is serving you. Okay? So these are challenges on the developer side, not from the user side. Of course, user use the system, they want this, but then how do you implement it? So this is the problem for the developer to figure out how to solve it. Okay, I mentioned to you just now that one of the useful benefit is fault tolerance. You have multiple server. If it is down, then you can actually access a different server, and you can get the information immediately, even though the data is down. Meanwhile, the system is being repaired. You are still able to use the system. Okay? There's no downtime there. Another thing is latency. The replication that I mentioned to you. If let's say everybody is using it, you replicate one copy near to the customer, so that you have low latency. Low latency means low delay. Whenever you access very fast. Okay, you can achieve that by replication, and then you move the data closer to the customer. So that is one of the good things about distributed system, okay, because you can move things around. Okay, how do you implement it in hardware? So there are two ways to implement it. The first one is to use tightly coupled hardware. The second one is loosely coupled software. Hardware architecture. So what does it mean? The picture there actually show some. Okay, here you see the diagram here is not very clear. This is one system. Okay, it can be one computer. One computer, but you have multiple processor. Okay? Multiple processor or multiple core in the processor. Okay? And each one of them will have their own, cache memory and also shared memory. Okay? And this is a tight system because it is in one system. Okay? You have shared memory, and therefore the access is going to be very fast. Another way to implement the system is to create loosely coupled system, like what is shown at the bottom there. Okay, you got different CPU here. Here is one computer, this is another computer here, and it's connected through the network. Okay, so you are connected through the network in order to create the computer system. Okay, this B here is leaning towards the distributed system. The first one actually is not distributed system, but it's parallel computing, because you got multiple computers. Okay, so this is basically used for vertical scaling. Okay, this one is used for horizontal scaling. When you have horizontal scaling, you add CPU, and then you need to network them together. That's why you got a network there. Whereas the tightly coupled system is meant to build vertical system. You have one system, and then you keep on upgrading that system by increasing the speed of the CPU or add the CPU in the system. But of course, when you add, there's some kind of limit. Maybe you get only 4 processor in the system or 16 processor, and then you cannot increase anymore. Okay, if you use loosely coupled, you can increase as many as your network can support. Okay, there's a story about this loosely coupled system. When the two founder of Google, okay, Larry and his partner, they were studying in one of the prestigious university in US. They were thinking about having this kind of search engine. Okay? Before that time, it was Yahoo. Yahoo was rising, and then they found Yahoo not so user friendly, and it's very hard for user to find information. So they have the idea of their own search engine. So when they try to implement it, of course they don't have money, right? They are thinking about scalability and also able to do it cheaply. So how do they do it? They don't go for the first option because the first option is very expensive, right? They know that their customer base is going to increase and they cannot keep on upgrading and buying a better and better processor. They don't have money because they are students, right? So what they do is they go to second-hand hardware shop. They go and source for the computer that is sold cheaply, reuse it. So they bought it, put it in the what they call it, their room, their own dormitory, and they hook it up using cheap network, internet. Okay, and then they implement the search engine there. Okay, and that is the first search engine that was created. It was inside their dorm. It's the same for many companies, in fact. Okay, like Apple, also the same thing. Steve Jobs and Steve Wozniak is his friend, also the same thing. They did it in their garage. And the other company that is also very successful now is HP, right? You heard of HP. HP also the same, by two engineers, Hewlett and Packard, also inside the garage. In fact, Steve Jobs, he was inspired by HP. That's why he created in his own garage as well. And he contacted HP to get support. Okay, either one of them, I cannot remember. He contacted Hewlett or Packard, I cannot remember. But Hewlett Packard at that time, he was doing well, and he realized that Steve Jobs is a bright person, so he helped Steve Jobs. That's why we got the Apple computer, right? Okay, so when you start small, you try to start in a manner that you can do it cheaply. Okay, so you don't start with tightly coupled. Normally we start with loosely coupled. So let's look at the tightly coupled system. What do you have inside there? You have high-speed backlink bus in order to make sure that your processor is able to communicate with one another fast and also to communicate with the memory fast. So you need to have high-speed backlink bus, and this is not cheap. Okay, only specialized company is able to do this. Like for example, HP, IBM, big companies that able to produce this, and they sell only not to us. They sell to big companies like Google and all that. So only big companies can afford it. So telecouple is not cheap. Okay, and the motherboard needs to be specialized. They have to specially created to support multiple processors. And when you build the motherboard, your architecture is fixed. That means if let's say you build for 10 processor, then it can only handle 10 processor. Okay? And again, if let's say you build for one specific processor type, then if let's say you got a more advanced processor with different kind of connection or interface, you cannot fit it into it. Okay, so to change the whole thing, it can be very costly. So that's why it's expensive to build, because it needs to be specialized. Second thing is, if you want to upgrade, you might need to upgrade the whole system. You cannot use the same system. You have to upgrade the whole system. You might be able to upgrade partially. You might need to sacrifice the rest of the system, and you have to pay for it. Okay, and the multi-core normally is very small. You got 4 cores, 5 cores, depending on the processor. And if you want to increase, you have to increase the number of processors. It depends on the motherboard that you have. Okay, if you want to scale vertically, it's not so easy. Okay, but one advantage of this tightly coupled is fast, because when you access, you don't have to go through the network. You've got a high-speed bus. The high-speed bus in terabit per second. Okay, not gigabit in terabit, maybe petabit per second even. Right? So your system is going to run extremely fast, your shared memory is going to be very fast, although it's expensive. It's going to be faster than distributed system. Okay, sorry, loosely coupled system. Now, loosely coupled system, because you buy off the shelf, not just like Google, you buy second-hand computer, which nobody wants to use already. They buy it, and they hook it up together through a network. And the hardware you can source abundantly, not just like what I mentioned to you, Google does that, and you can buy it cheaply, right? In fact, they use their own pocket money to buy it. That's how they did. Actually, you can go to Wikipedia and see they still they capture a photo of how Google, the two founder, built their system. It's still there in Wikipedia. You can check it. It's actually in a stack it in a tray. Sorry, in a cabinet. Okay, so loosely coupled is cheap. It's abundant. You can source it easily. And when you scale horizontally, it's much easier. You want to add how many processors is up to you, as long as your network is able to handle the bandwidth, the data bandwidth that is generated. Okay. So loosely coupled system do not have its own clock, so you have to synchronize them. It's unlike the tightly coupled system. You only have one clock. Everybody share the clock, and everybody has the same speed, or maybe different speed, but then they are synchronized. Okay. Whereas loosely coupled, they are not synchronized, so it can be a problem. Why synchronization is important? Let's say, for example, if you do banking, right? If you have shared account, suppose you have shared account, your brother and yourself, let's say. Okay, you have a shared account, two names. You've got two ATM card. One of your brother is living in maybe traveling to America, and you're here, and you access your bank, you retrieve the money, right? Your brother also retrieve the money almost at exactly the same time. Now, if the bank system, distributed system, is not synchronized, what is going to happen? If they withdraw at the same time, let's say the bank balance is 1,000 ringgit. I withdraw 100. He also withdraw 100. The first time when we withdraw, we see 1,000. He also see 1,000, right? And then when I retrieve 100, my brother also retrieve 100. If there's no synchronization, then there can be a problem, because everybody is looking at the money, which is 1,000. And the bank also have problem because they are not synchronized. Okay? Maybe if I retrieve 100, maybe it's not a problem. But let's say I retrieve 1,000, all the money that I have. My brother retrieve 1,000, I retrieve 1,000. Is the bank is going to approve both? If they are not synchronized, that means approve this, approve my brother as well. So both of them earn extra 1,000, right? So synchronization is a problem. Whereas in a tightly coupled system, there's no problem, because every processor is synchronized using one clock. Okay? In distributed system, if you see this graph here, everybody has their own clock. Okay? So the timing is kind of important, because the transaction, every time you withdraw your money, you see your slip, there's a time there, right, when you retrieve it, right? So the time here is quite important. You need to be synchronized to make sure that when you retrieve, who actually should retrieve first. And if, let's say, it's already retrieved, make sure that it cannot be retrieved the second time, right? That means your program needs to synchronize to make sure that you don't lose money in the case of the bank. Okay, the challenges of the loosely coupled, just now I mentioned about the synchronization, because it's loose, they have their own timing. They have to make sure that they are synchronized. There are ways to do that. We will cover some. How to synchronize the time, so that we don't have this kind of problem. Okay, another challenge is you need to make sure that the computer are autonomous. That means they have their own authority. That means they are intelligent on its own to do some decision making. Okay, so when you give command, they can do it in distributed manner, not in centralized manner. Like, for example, banking. if one ATM is allowing you to retrieve the money, it needs to communicate with the ATM in Malaysia and make sure that I don't retrieve the money as well to the limit. Okay, let's say I retrieve 1,000, the other, my brother is also retrieving the money. Okay, it needs to synchronize and make sure that the decision that is made is correct. Okay, so autonomous, meaning that they make their own decision, but they make the correct decision. And another challenge with the loosely coupled system is heterogeneous problem. If you buy a computer, let's say tightly coupled, if the processor that you buy, most of the time you buy the same one, right? Because the board that you buy support multiple processor, you buy all the same. Let's say Threadripper, all Threadripper, okay, of the same model. But then if you buy loosely coupled system, it depends on availability, right? For example, you cannot expect that, let's say Google, the founder, Larry, let's say Larry go and buy from the shop. You can buy, you can secure maybe 100 units of computer, which is Dell. And then another 100, he has to buy maybe HP because out of stock already. Okay, so when it comes back to his dome, is constructed or maybe build it up, you have a computer with different kind of spec. Okay, heterogeneous means different specs, and you must make sure that this different spec is able to work together. Okay, this is not a problem in tightly coupled because tightly coupled you already specify that you have to buy that processor, right? But loosely coupled, there's no such arrangement or agreement. You can buy any kind of processor or computer and just put it. You must make sure that they still able to communicate with one another. Or maybe one is running Windows, the other one is running Linux operating system. But you must make sure that they are still able to work together. Okay, so that is a challenge for the developer to ensure that. So what is the motivation for loosely coupled distributed system? The motivation is because you can share large amount of data, okay, without needing to buy only one hard disk, which is extremely large. You can buy multiple computer, which come with its own hard disk, and then you can share this hard disk space, okay, or the storage space. Another thing is the motivation is what we have mentioned. You can buy cheap workstation or computer where you can get off the shelf, maybe second hand. You can buy cheaply. And also you can share the expensive peripherals. Peripherals here means device. For example, let's say GPU. Let's say, for example, I was talking about our lab, right? Our lab, we have GPU, of course. But if, let's say, you go back home, you want to do your work, you don't have GPU at home, right? Okay, some of you don't have GPU. I mean, NVIDIA GPU. So how do you do the work? Then you have to get the resource somewhere, right? So that resource is maybe Colab. So Colab has GPU, and the idea is to share that GPU. So it's shared with me, you can share with you as well. So if I'm not using, you can use it. Or if you're not using, somebody else is using it, right? So the idea of the distributed system is to share the resources. So you can have GPU in certain area. Okay, if I want to use it, I can use that expensive resources because it's not cheap. GPU is very expensive because of AI. AI make the price extremely expensive to afford the GPU. So you can buy the GPU for some server, but not all, for some of it. And whenever you need it, you access that server. Okay? And you see this in Colab. When you start the Colab, normally you start without the GPU. Okay? So when you want to do the exercise with the GPU, you find out that it cannot run. It can compile, it can run, but it will not give you the result. The result is incorrect, okay? Because the GPU is not there. So in order to use the GPU, I need to click a button to enable the GPU. And then because it already creates the instance, my instance, on the computer without the GPU. So you have to shut it down, move it to a new computer, and that computer has the GPU, and then start all over again. Okay, so it will migrate. So all this requires migration and all that. But the gist of what I'm trying to say here is you can actually share your resources. Whenever you need it, you can share. Because it's expensive, you don't have to buy upfront for everybody. You know that everybody is not going to use all the time, right? Sometimes this group is using, sometimes it's not using. So when it is not using, you can pass around to other people to use, right? So you can buy expensive hardware, and then you share them. Okay, so if you need to share expensive hardware, Lucid coupled system is the best way to go. Okay, in fact, Colab is actually using Lucid coupled system. Okay, and then another thing is nowadays, because we have very cheap high-speed one. When I was a student at the time, network was new to us. We only have 64 kilobit per second. Right? But right now, we're talking about gigabit, maybe petabit per second already, right? Now gigabit for everybody is normal. We are looking into petabit per second. During my time, it's kilobit per second, 64 kilobit, maybe 32 the first, 32 kilobit per second. And when you get connected, you can hear the sound, the sound, because we use modem at the time, use telephone to get connected to the internet. Okay, so cheap hardware right now, you can buy very cheap, right? You buy a router, how much is it? Wi-Fi router now? Maybe they give you free, right? You subscribe to the telco, they give you free one router, is that true? Because it's so cheap, right? During Google, it is considered cheap as well. When Larry bought it, it was cheap, that's why he built the system using Lucid coupled system. Okay, so another thing is another motivation is to allow you to communicate and interact with multiple users much easily. Let's say, for example, Colab that I was talking about is Lucid coupled system. You can communicate, you can share the resources easily. Okay, and if you want to scale, you can scale easily as well. So there's a flexibility of growth. Okay, and then you can provide the service to the user much faster because it's Lucid coupled normally is distributed system, and normally the distributed system is close to you, so you can get the service with lower response time. Okay, this one shows to you the hardware that is shared. So for example here, you got expensive machine here, and then your storage you can share using this workstation server model, which is a Lucid coupled system. Okay. Another good thing about distributed system is you can create a compute system and share that compute system. Like for example, Colab that I mentioned just now. I don't use, when I run my program, I don't run on my computer. I run in Colab environment. So actually Colab is instantiating the compute system for me to use. Okay, and of course if I pay, I get better service. If I don't pay, I get not so good kind of service. Okay, or maybe a limited amount of time to use. So you got a pool processor, which is Colab is a good example. If the computer is not used, you shut down to save power. If let's say a user comes in, then you bring it up and then share the compute power with the system. That's how cloud service or cloud computing works. Okay. Something related to cloud computing is grid computing. not sure why cloud computing is not there, but grid computing is there. Maybe it's up here. No, it's not there. Okay, grid computing is something similar like cloud computing, except that grid computing is shared resources by user. Cloud computing is more for the company to build a server farm, and then they give you the server. Of course, you have to pay them. Grid computing is same idea, except that the computing does not come from one single company, but it comes from the user like me or you. Okay. One good example is the I cannot remember the name of it, but it's actually to find or to use your processing power to study the signal that they gather from the sky, okay, to look for alien. Okay, and what they do is they have a program where you can download, and it runs in the background of your computer. So you can actually download it. It runs in the background, and then that program is connect your computer to the server. Okay, so that it can download any specific software to your system and run in the background to use your processing power. Okay, so this is free, meaning that you as a user, you give free service to the community. Like for example, since like I mentioned to you, to find the signal from the space and all that, it's actually a collaboration between the organization and the community. So if I want to participate, I just download the software, run in the background, they will use my extra processing power. Maybe at night I'm not using, then you use it. Or maybe I'm heavily using it, it will slow down a little bit because I'm using it. Then if let's say I don't use the computer, then you increase the compute power for the system to use. Okay, and this is also useful for drug discovery. There are some organizations, like for example university, they have this kind of program where you can download the software and you run in the background. You do not need to know what they're doing. It's fine. They also don't want you to know what they're doing as well. So what they do is they send the data to your program that you download, and then you process it to discover drugs. Okay, drugs to cure certain kind of disease, because they need compute power and they do not have money, for example, to build the system. So they ask the community to help. So this is grid computing, something like cloud computing, except that is for community purpose. That means you help one another in order to advance the discovery of things, or to expedite the discovery of certain research. Okay, so they use distributed system to do that. Now, another challenges, or one of the big challenges of the distributed system is transparency. So the transparency here doesn't mean the transparency that we hear always in politics world. Transparency here means, as a user, when I use, it's transparent to me. Like for example, if I use the computer, I don't need to know where my program run. It can run on, let's say, a computer in Malaysia, or it can run in America. It can run anywhere. Okay, but it's transparent to me. It's not transparent to the system, but it's transparent to me, because when I access, I don't need to know all this, right? I don't need to know all the details, where my system is, where my data is. I just need to know whether I can compute and can solve the problem, and whether I can get the result, right? So that is the meaning of the transparency here. And the developer who developed the system has that problem, because you want to make it transparent to the user, ease of use. So you have to make sure that this is not revealed to the customer. Okay, so whenever the customer access, he can access easily. For example, Netflix. I don't have, as a user, I don't have to tell the system, the Netflix system, please duplicate a copy nearby here so that I can watch easily, or the response time is faster. The system will do it automatically. So once it detects that you are in Malaysia and the bandwidth is limited, and a lot of people watch that movie, so it will automatically move the video from US to Malaysia automatically. So it does this transparently. Okay, that is the meaning of transparency. So you have to be transparent, make sure that is transparent when you move. You must make sure that when you fail, you can recover easily. Okay, and then the data, when it change, the data is changed. I said the movie is, or maybe the program, I said not movie. The program is patched, then every replication is also updated as well. So you're not having the old copy. Because when you replicate, you might have a stale copy, right? Let's say in US, I duplicate it in Malaysia, and then somebody update the copy in US. So you must make sure that the system needs to transparently make sure that the data is also updated in Malaysia as well. Okay, so that the data is consistent. So you have to ensure that the consistency is there. Okay, and then when you build the scalable system, let's say you add a new system, right? You can actually move the user from the old system to the new system, and you have to do it in a transparent manner as well as you scale. Okay, so as you add, the user will not know that the system is upgraded. Okay, and your data can be moved anywhere as the system finding better to do. Okay. So the transparency is actually hiding the details from the user, so that you don't have to know what is going on. But of course, this is to lift the burden from the user, but it actually increase the burden on the developer. Okay? The developer have to make sure that the transparency is done well and without any hiccups. Right? So the transparency that I touched just now is access transparency. For example, I access Microsoft.com. I do not need to know whether I'm accessing the American headquarter server or Malaysian headquarter. This is done by the system. You move my request to the appropriate server according to my location. So that is access transparency or location transparency as well. Okay? And another thing is, let's say if I run my system, I don't need to know that it run the system in parallel or in concurrently. Concurrent means you run at the same time. Okay? So let's say when I solve a problem, it can be broken down into multiple sub-problems and then solve them at the same time. I don't need to know that. I just submit my problem, and then the system will automatically or transparently break it down and solve the problem faster using a distributed system to do. Okay, replication I've mentioned many times. You replicate is as you need. Like for example, Netflix. Okay, depending on location, you replicate it. Failure also mentioned many times just now. Your server failed, automatically the system needs to recover quickly, and this is done transparently by this distributed system. And another one that is closely related to replication is migration transparency. Maybe this one is something related to collab I mentioned just now. When I use my collab, when I start the system, normally it will give me a server without the GPU, right? And then when I use this GPU, you move my program to the server that has GPU, and you run that. Okay? I don't have to do much. I just need to click a button. But that one actually is not transparent. Here, transparency means when I run the program, automatically it does that for me. You move without telling me that it has done the migration. Okay? So as a user, I see that I'm using the system. I don't move anywhere. But at the back end, actually it moved my process from the server without the GPU to the server that is having the GPU. Okay, so that is transparency migration. Alright? At the moment, Collab don't have this. Right? It doesn't have a full migration transparency, it has partial. I need to click to tell that I want to use GPU. That's the first thing. Second thing is when you migrate, you destroy the data and you restart the whole thing again. Okay? So that is not transparent. A transparent one will be you move without restarting. Okay? That means it run my program. Halfway it run, it discovered that it's to use the GPU. It migrate without me knowing it, and then run on the server with the GPU without stopping. You continue on. Okay, so that is a full migration transparency. Okay, Google Colab do not have full transparency; they have partial migration transparency. Another one is performance transparency. For example, I use the server, and then a lot of people use the same server. Now it gets overloaded, and everybody will feel the performance degradation, right? Let's say initially I use only one person using the server, so it's fast. Then 10% start to use it, so it degraded by maybe 10 times. Then another 100 comes in, let's say for example, it will reduce further. Okay. Now, of course, the system, if let's say the system poorly built, without performance transparency, now you feel that kind of degradation. Suddenly you find the system getting slower and slower. If you have performance transparency, the system is intelligent. Now when they see that the server is overloaded, you migrate some of the user to other server, so that you will not degrade the performance. Okay? So whenever you detect that the performance is degraded, it start to shuffle around. Okay, so that is performance transparency without telling you that things are being changed in order to improve the performance or to maintain the performance. The scaling performance transparency means when you scale time, you don't have to worry about telling the user I'm scaling right now and I need to maybe stop your program. No, I don't have to do that. I can just scale without stopping your program. So your program is still running, okay? And your program might be migrating to a new system that has been installed also without telling you as well. Okay, so this is scaling transparency. Okay, now we are reaching another part of the system. This one actually has nothing to do with what we have discussed just now. It's about a real-time system, why we need a real-time system. In the distributed system, when we do distributed system, most of the time we will have to coordinate with one another, right? So when you coordinate with one another, you need to have instantaneous sharing of information. If let's say something has changed, okay? So you need some real-time system implemented in the system itself, so that the distributed system is aware of one another if anything goes wrong or anything that is changed. Okay, one of the example distributed system is in your car. Do you know how many processors in your car? Modern car, not the cheap car, the expensive car. Okay, let's say one BMW. Anybody can guess how many processors in there? Okay, it has more than 100 processors in there. Okay, so it has more processor than your computer. Okay, it's distributed all over. You have one processor maybe for your window. Okay. On all four, you got four there already. Your engine, the engine that synchronize the piston and all that. It's called engine management unit. There's one processor there as well to control the engine. It has a processor for your brakes, for your airbag. In fact, your keychain, the fork that you use, has processor in there also. Do you realize that? It has program that is running. Okay? So basically, every of our system has a processor. So it's distributed. You need to communicate real time in order to get things done correctly and also on time. Because you don't want like you move to the car and then you have to wait for a while for it to unlock. Right? So you need a real time kind of response. Okay, real time does not mean fast. It means something that is acceptable. For example, if I move my mouse, it does not need to do it in picosecond. Picosecond is 10 power of minus 12. Okay? Second, 10 power of minus 12 second actually is very fast because the processor is 10 power of minus 9 at the moment. It's gigahertz, right? So you don't need a picosecond kind of response time, but it's something that is acceptable. For example, if I use the mouse, maybe sub-millisecond is good enough, right? I don't want to wait 1 second, but 1 millisecond is good enough. Anything below 1 millisecond, I don't feel, because it's more or less the same to me. Okay? But if let's say you're talking about, let's say talking about the car piston. The piston is moving very fast, right? So you need to respond very quickly. Because if you miss it, then you fire at the wrong position. It might damage the piston and also the engine. So you have to fire the engine at the correct time. So that will require real-time system. Okay. And of course, when we talk about real-time system, in our case, we have to talk about distributed real-time system. We have to share the information in timely manner, so that we don't have problems. Okay, like for example, in the ATM example that I mentioned to you, the information needs to be shared in real time and on time, so that no mistake is done. That means I withdraw 1,000, and my brother is not able to withdraw 1,000, okay, at the same time. So this information needs to be passed along in the distributed manner. It needs to be done in real time. Okay, and of course you have to manage this properly in order to make it successful. Right, I will not go into this because I mentioned this multiple times. This is just to show to you that you got multiple nodes here, and then you got real-time communication system. In a car, we don't use Ethernet. We use something similar like Ethernet. It's called CAN. Okay, CAN. I'm not sure what it stands for, but the protocol is similar like Ethernet. Okay, it's slightly slower, but it has priority. So let's say, for example, if I use my button to control my windows, right? I want to lift it up or bring it down. The priority might not be as high as the engine. Okay, so whenever the engine sends a message, it has to send in real time. So you tag the messages with priority. Let's say priority is number 0. So the priority 0 will be service first. The one that I use to control the window would not have so high priority, so it will be given a lower priority. So the message will wait until all the high priority messages has been serviced, then only start to get distributed and use the network system. Because the network system memory is not so high in cars, so you have to prioritize the messages. Okay? So specific issues with the distributed real-time system, like I mentioned to you, it has its own clock. You have to synchronize the clock. Okay. So in real-time communication, we have the clock that needs to be synchronized, and we have several algorithms to solve this. And 2 algorithms we're going to discuss here. The first one is called Christian algorithm. Christian is not religion. Here is the name of the person, Christian. His name is Christian. He's a computer scientist who actually first mentioned about this algorithm. That's why the name is given to him. Okay, Christian algorithm. And the idea is very simple. What you want to do is you want to share the time. Make sure that the time for this machine and the other machine is synchronized. Okay, so you want to synchronize this sending machine time with the server time. How do you do it? Okay, first what you do is you send a request. Okay, you send a request. That message will travel across the network, and the server might not be nearby. It can be very far away, maybe across the continent. It takes some time to travel. Okay, so that's why you can see that the time is progressing downward, right? Okay, progressing downward. As you send the request, the time actually progress. So by the time when you reach the time server, the time has already passed. Okay. So this T0, this might be, let's say T1, sorry, T1 is already here. Let's say TA. Okay, so there is time that is already passed between T0 and TA. Okay. Now, when the server responds with its own time to the sending machine, so this sending machine will get the time that is specified by the server. Okay? And then you use that time to update its own time so that now its time is synchronized with the server time. Right? So what is the problem that you see here? T0, at T0, this machine tried to synchronize the time to the server. So imagine the server is the correct time. So the sending machine want to update its own time so that it corresponds to the time of the server. But remember that when you send a message, actually it needs time to travel. Okay, the message needs time to travel. So by the time when you reach here, okay, the time has passed and it get the time and send it back. So when the sending machine receive it, does it receive the correct time? Does it receive the correct time? No, it doesn't receive the correct time. It receives time that is not quite right. Okay? So let's say for example here, I draw a pen, maybe I will draw it. Bring my pen. I think there's a board here, right? I can't remember what it is. Right here. I think you remove it already, right? Can't find it there. How come I don't have Is the Jamboard down here, right? Okay, we got T0 here. Okay, never mind. Maybe I'll draw with mouse. Because I can't draw with mouse. I'll draw with mouse at the moment. Yeah, draw it here. So you got T0. And you got time that is sent to the server. Let's say this is TA. And then this one comes right here, right? This is T1. Anybody has a pen that I can borrow.
可以记得。够。放哪个光我觉得
Cannot use this channel. I think they'll go to discontinue.
然后大家吃完饭，我马上就吃了。
Maybe I just roughly try my best to draw it.
不管
You got
这个
T0,
错，
you got
一完了
T8,
就停掉了。说一完我就停
then this one is T1.
我讲这个是交易唱片，唱个屁呀！
Now suppose here, when you request, okay, let's say your time here is
好，下个拜一我再搞定。是啊，我拿
3 seconds, let's say 3 seconds, simple,
拿
right?
起来跟
3
写的
seconds.
无关。
Maybe 30 seconds. Okay, this time here is 30 seconds. But when you request, the first time when you request, okay, at this time here, the server actually is,
这样的吗？这也是。
let's say 28 seconds. So it requires 2 seconds to travel, right?
这个拜一可以搞。
Okay, it requires 2 seconds to travel. Now, assume that the network is the same forward and backward. That means it requires also 2 seconds to come back. Now, this is not necessarily the case. We're just assuming. In Christian algorithm, we assume that these 2 seconds going and coming back also the same amount of time it takes. Okay, and of course this is not always the case. But 3 seconds, it can be 4 seconds, it can be even faster, right?
骗我吧，你骗我
But。suppose that we assume the time that is taken for it to go and come back is the same. So when you reach here, what is the time here?
这个是知道来的，是对我们。
Is 32, isn't it? Is it 32? Right? So what is given to you, the message that is sent back is 30. Do you take that 30? Because if you take that 30 and you start your time here, 30, is it correct? It's not correct, right? Because the time has passed. The server time has already gone to 32 and you are 30 here. So it's incorrect. So how do we estimate? Estimate the time of your server. The problem here, why we got this ambiguity is because of the traveling time. Okay, the propagation of the message to and fro. Okay, so it takes 4 seconds to reach back here. Okay, when you receive 30, you shouldn't start here 30 because if you put 30 there, you start with 30, the actual time is already progressed to 32. So what is the formula here in order to get the correct time when you start your time here, or you correct the time here? Okay, what you do is this. Because the time progressed from here to here is 4 seconds, right? Right? Let's say your time actually, sorry. Let's say your time here is incorrect. Your time is, let's say, 20 here, let's say, right? But the time when you reach here is also 4 seconds, is 24, isn't it? Is it correct? The time that progressed in the server and you is 4 seconds. But your time is wrong, 20 to 24. But the server is, the actual time is 28 to 32. Right? So how do you correct it? How do you estimate the time of this server when the message that is passed to you is actually outdated one, is 30, which by the time that we receive is actually wrong. Now you want to estimate it. So what do? You take T1 minus T0. Because you assume that to and fro is the same amount, so you divide by 2. Okay, so what do you get there? T1 minus T0 is 24 minus 20. What do you get? You get 4 divided by 2. You get 2, isn't it? So when you receive 30 here, what you need to do is just adjust it. So you get 30 plus 2 plus this 2 here. And that's why you can estimate the correct time, which is 32. Do you understand what I'm talking about here? This 2 is this 2. This 30 is this message that is passed to you. And the correct time that you estimate is 32. Do you understand? Okay? The idea is this. You do not know the actual time. You only know your time. The time that is progressed in at your place is 4 seconds. It's the same as the time that is progressed in the server, which is 4 seconds as well. Alright? So you take that difference, T1 minus T0, divide by 2, you get 2 seconds. That 2 seconds is the adjust time that you need to apply to the message that you receive. So 30 plus 2 is 32. So basically, you can estimate the time by correcting the message, the time in the message, so that you end up with the correct time. Do you understand? Okay? So whatever formula that I showed to you here actually is T1 minus T0 divided by 2 plus the time that is gotten here. And that is what the slide is telling you. Where is the slide? You see that? You see that formula there? The bottom formula, T1 minus T0 divided by 2. That C is the time that is given by the server. Okay, but the time that is given by the server is already stale. It's wrong. You have to correct it. How do you correct it? You correct with that formula. You understand? If you don't understand this, look at this picture, the one that I explained here. Okay, you want to snap photo, you can. I can share with you also this. Maybe I'll share to you later. Right? You get it? Okay, so the Christian algorithm is all about that. Do you have time? I will finish at 12, isn't it? Okay, now we go to the second algorithm. Actually, okay. Here's a good question then. What if the time, the request time, that means the traveling time here, because I assume that is 2, isn't it? 2 and 2. Suppose it's 3 and 2, how? If 3 and 2, that means it's incorrect right now. Right? Because here 3 and 2, that means here should not be 30 anymore, it will be 31, right? So when you receive 31 and then when you compute, it's going to be wrong. Yeah, it's going to be wrong because Christian algorithm, you have some ambiguity about the traveling time. You're just hoping that the time travel to and fro is the same. Okay? Assuming that the path that is taken is the same. Let's say, for example, if your message comes from America, so you send to America and come back, is more or less the same. Okay, you have to assume that. But of course, like what you say, we cannot ensure that this is correct. Okay, so there is some mistake there, but we hope that the mistake should be is small. We don't want it to be too large. Okay. In fact, your system is actually doing this all the time. Do you know that I'm not sure about the car system, but there is some clock inside. You open it up, it has some antenna. That antenna is actually receiving the signal from the tower. the tower keep on sending the time. So you update the time. So you bring that clock to a different country, the clock actually will change to the time in that country. Because the other country also have the tower to send that same, because it's a standard, you send that signal. So that clock is actually receiving the signal for wirelessly and then adjust its time. Okay, so it basically use the same technique here. Okay, and in fact your computer, let's say for example when you start your mobile phone, right? And you also request the time from the NTP. NTP is network time is actually network time protocol. There's a server. You use NTP to request for the time, and then you do this adjustment as well. Because when you request and it comes back, the time is already different. So you make the adjustment using crystal algorithm. So crystal algorithm is used in our mobile phone as well. Okay. And we assume that the time progress, the time that you send and receive is the same. So the crystal algorithm solved this problem. It solved the synchronization problem. Okay, but of course, it will not be very, very accurate. Okay, we hope that it's accurate, but it can be slightly different from the actual time. Okay, and here we assume that the network delays is the same. If it is different, then of course it's a problem for crystal algorithm. Okay, so this is a question that you asked just now. Okay, and then the processing delay of the computer might be different as well. Let's say for example the computer and server, when you receive, it will not send the message immediately. Okay, you do some processing before it sends. So there is some kind of processing delay that we do not take into account. But we hope that the computer is fast enough. Whenever you receive the message, you immediately send the time immediately, okay, without any delay. So if we make sure that this one is small, the network delay is small, there is no time varying, then the crystal algorithm will be more or less accurate. Okay. So just now I was talking about, I got 7 minutes. Just now I was talking about time that you synchronize according to the time of the server. Okay? So we want accuracy. We're talking about accuracy just now. Okay, accuracy. There's another point that we need to take into account. The other one is precision. What is the difference between these two? Precision and accuracy. Sorry, I have to try like this. What is the difference between accuracy and precision? Okay, if you want accurate, let's say this is your target. Okay, sorry. And you throw darts. And it hit here. So this one is called accuracy because the center point is the point that we are targeting. Okay, and you see that is quite accurate, right? Now, if let's say I throw my darts and it happens to be here, is that accurate? Is that accurate? It's not accurate. But within this group here, there's high precision. Even though I'm not accurate, but I precisely hit that point. Okay, so the accuracy and precision, the meaning is that. Alright? Now, crystal algorithm, what we want is accuracy. The other algorithm, which is the Berkeley algorithm, which is this one, we don't really care about the accuracy, we care about precision. Okay? Because sometimes precision is more important than accuracy. For example, bang. Maybe the accuracy is not important, but the precision must be correct. That means the time must be very close by with one another to make it correct. Okay? That means you don't dispense the money twice. Okay? You want it to be dispensed one time only because your time, your precision is accurate. Okay, but your accuracy might not be, might be out. Maybe the time is off. Like for example, this picture here, the time is out because the accurate one here. But then everybody has the same time. That means they are precise, not accurate. Okay, but if they are here, then you're accurate and you're precise. Okay, yes, as center here. But unfortunately, both algorithm cannot provide both. Okay, one Christian algorithm you strive to have this, but you might not have precision. You can have accuracy but not precision. But the other algorithm, the focus is actually precision rather than accuracy. You don't really care whether you are precise, accurate, but you want it to be precise. So this algorithm, how does it work? I've got 3 minutes. What it does is this: the master will request the time from the slave. He requests the time from the slave. Okay, he requests, and then the slave will return back his time. Okay, he will return back his time, and then the master will take the average of this time. Okay, and then apply. Okay, apply to all of them. So right now, the server, the master, actually don't care about accuracy because it changes its own time as well. It finds the average of all, and then it disseminates these messages to all of them. So it changes time. So its time is not accurate anymore. But what it wants here, the goal here, is to make sure that all of them, including the master, have the same time. You understand? You understand what I mean? Because when you find the average, your time is off already, but it doesn't matter. But what matters here is the slave and the master and all the slave has the same time. Okay, so here is the precision rather than the accuracy. You understand? Okay, so this is another algorithm that is used in order to synchronize the time. Okay, you synchronize based on accuracy, which is more important rather than the accuracy. The precision is taken into account more than the accuracy. Okay, so the step is like what you like Christian algorithm, except that it requests, the master will request, and then the slave will return the time, and then the master will compute the average, and then he will update the slave. Okay. Now, when you update the slave, it does not send this. It sends only the difference. Here, I think there's a mistake there. It does not send the time, but it sends the difference. So here is 3, right? And then when you calculate is 5, isn't it? It's 5. Okay. So when it's sent to the slave, it's sent -5. Because here is 310. The -5 is 3.5. Okay, so there's a mistake in this diagram here, which is not so accurate. It does not send the time, it sends the difference. So you tell the slave, you reduce by 5. So the slave take its own time, and then -5. So you get 3.5. Okay? And then you tell the slave number 2, slave number 2 is 250, right? So it will ask slave 2 to add by 15. So it will send 15 to slave 2. So slave 2 will add 250 plus 15. So it becomes 355. Slave 3 is 320, right? So it will tell slave 3 to -15. So it will send -15 to slave 3. It does not send the time, it sends the difference. Okay? There's a reason why it sent the difference. The reason is because of the Christian algorithm, because you have delay, right? So if you send the difference, then the other slave don't have to compute using the Christian algorithm. Okay? If you send the time, then you have to compute, and then you have error, another additional error. Okay? So there's only one error. The error is only when the slave sent to the master. That will use Christian algorithm to send, and then the master will predict what is the time of this slave using Kristen algorithm. But then when he update the slave, he does not use Kristen algorithm anymore. He use the difference. Because if you use the difference, you don't have to worry about the time delay and all that. Okay, so there's one error. The error is only from the slave to master. But from master to slave, the message is only the difference, and therefore there will be no mistake. Okay, so that is the only difference between a Berkeley algorithm and Kristen algorithm. Okay, let me tell you now first. The exact question will have this, so pay attention to these two algorithms. Okay, this is the formula. This formula is correct. The diagram here is incorrect. Okay, so you just need to adjust it. Okay, I finish here. Oh yeah, I forgot to take attendance.
DOS tu不懂，他没讲，他讲一个 DOS 不好，还建议他